Hello, and thank you for tuning in to our virtual presentation on our 2023 FACT paper, Add-Remove-or-Relabel Practitioner-Friendly Bias Mitigation via Influential Fairness. My name is Brianna Richardson, and I'm happy to be here presenting on behalf of my team. In my short time with you, I intend to discuss the motivations behind our work, some surface level background to highlight the problem space and our proposed fairness solution. I'll also highlight some of the results of testing our proposed solution and end with some conclusions and future work. Machine learning is prolific. You can find automated processes within nearly every industry, from health to entertainment to government and politics. When left unchecked, bias often impacts the performance of these algorithms, inevitably perpetuating new biases and reinforcing old biases within society. Responsible AI is a collection of efforts built to counteract bias and prevent it from influencing the algorithm. Fairness in particular aims to detect and mitigate sources of bias. Despite the large quantity of fairness solutions, practitioners often don't use these tools in practice. A number of works have studied practitioners and gathered their thoughts on algorithmic bias efforts. Practitioners voice concerns with complicated solutions, irrelevant strategies, and overly flexible types of manipulation. It is worth reiterating the fairness research space is expansive. When surveying the bias detection space, Furman and Rumit isolated 20 distinct measures that could be utilized for bias detection. When surveying the bias mitigation space, Catan and Haas found over 100 different mitigation methods that differed in technique, measure, optimize, and the implementation stage. Despite this prolific number of fairness contributions, again, there still exists a gap between the fairness experts and the machine learning practitioners. Now I'd like to introduce a concept that's fairly new to the machine learning space, influence functions from robust statistics. Influence functions are a relatively faster way to identify influential instances. An influential instance is a point that, if deleted from the dataset, would greatly impact the predictions of the model. The organic way to compute influence scores is to remove a sample from the training subset, retrain the model, and see how predictions change before and after the deletion. This obviously is not realistic for most use cases where models are complex or the number of training points are large. Influence functions recompute model parameters to derive influence. By upweighting the loss of a training sample by a very small amount epsilon, we can approximate the loss using the gradient and the Hessian matrix. Here I show the final equation for influence of a training point Z on a test point Z test that is calculated using the Hessian and two loss gradients. This original work was done by Ko et al. In 2017 and has been influential in the interpretable ML space. Recent work by Sattigeri et al. In this year's NeurIPS conference derived a formula for computing influence of a training point on an evaluation distribution ZT using a given group fairness metric M. By modifying the loss of the gradient in the original influence function, they were able to derive a new use case for influence functions. While they demonstrate these group-based influence scores can be utilized for removing bad data, our work aims to demonstrate how this same formula can be used to create a family of mitigation methods that are both transparent and cater to practitioner needs. In this work, we call these scores influential fairness scores. We have two objectives behind our work: to better delineate the needs of practitioners by creating user profiles, and utilize influential fairness scores to design profile-catered mitigation methods. After a literature review through works that elicited feedback from practitioners, we defined 4 profiles: the free-range practitioner, the data-limited practitioner, the protocol practitioner, and the auditing practitioner. The free-range practitioner, they have access to the model and the training data, they can access new data, and they're not limited by any rules. The data-limited is the same, except for they are limited in terms of access to new data and not wanting to get rid of the data that they have. The protocol practitioner is similar to the free-range practitioner, except for they are limited by the types of rules and restrictions that they have placed on them. The auditing practitioner, they have access to neither the training data and they have black box access to the model. Most works are built with a free-range practitioner. This comes to little surprise because most fairness experts are either free-range practitioners or auditing practitioners. Few works consider these alternate profiles. It's important to note that all of these practitioners would prefer to reduce the fairness accuracy disparity and minimize the amount of perturbations they're making to their data and their model. Prior to introducing my proposed mitigation methods, I'd like to clarify the stage in the machine learning pipeline that these mitigation methods are created for. Our method exists as a post hoc method, so once the model is made and group fairness scores are computed, influence scores can be generated, and then one of the proposed mitigation methods can be employed. Once that mitigation method is employed and the training subset is modified, you would retrain your model and iterate until you reach your desired results. There are 5 mitigation methods that I propose. These are designed to be understandable and simple methods. Opponents are samples that were found to worsen disparity, and proponents were samples that reduce disparity. The 5 methods that I propose are the removal method, which identifies opponents, removes them from the training data, the duplication method, which finds proponents and duplicates them in the training data, the addition method, which is very similar to the duplication method, except for it uses an estimator to predict fairness influence of points that weren't used in the training subset. And then those points are extracted from whatever held out subset they came from and added to the training data. Relabeling, where we take our opponents and we switch their label in the training data. And then our inverted nearest neighbor duplication, in which we identify opponents. We find the nearest proponent neighbor with the opposite label, and we duplicate that neighbor. Again, these methods were built with practitioner profiles in mind. Removal, which has been seen in the Sattigeri et al. Paper, is best for free-range practitioners, but tools like duplication and relabeling help people who are data limited. Furthermore, our addition is promising for protocol and auditing practitioners. We tested these methods on 3 datasets for 4 separate fairness metrics. Each of our datasets are benchmark datasets with renowned disparities, and our metrics are 4 standard fairness metrics. We trained each of these datasets with a logistic regression model. We had 5 experimental inquiries when it came to investigating these techniques. I won't be able to discuss all of these results for the sake of time, but I encourage you to browse our paper. I will, however, summarize a few of these results. Our first inquiry was whether or not our computation of ground truth scores was valid. When iteratively removing ranked proponents and opponents from highest absolute magnitude, we found that, as expected, removing opponents reduced disparity and removing proponents increased disparity. Next, we aim to identify the number of samples that we should modify to optimize outcomes and reduce the size of the resulting modification. We use our mean influence plot to identify the point of diminishing returns, also called the knee. We demonstrate that the knee of the curve can optimize final disparity, reduce loss of accuracy, and reduce size of perturbation. Skipping to our final inquiry, do proposed methods compete with existing methods with respect to disparity, points modified, and accuracy? Our conclusions confirm that they definitely do. We compared our method to the reweighing and relabeling methods by Cameron and Calders and the label bias method by Zhang and Naga. We demonstrate to the right how all mitigation methods perform for false negative rate on the adult dataset. In yellow, you will see the accuracy and disparity of the original model. In orange, you will see the performance of the 3 existing methods that we looked at. And then in purple, you will see the results of the proposed methods. The objective would be to get outcomes that are in this top left corner, where accuracy is maintained and our disparity is reduced. You can see that our purple methods do really well at getting to that point. This plot does not show the size of the modification required for each method, and I can confirm that our method perturbs significantly fewer samples than existing methods. I won't go into the performance of every single mitigation methods, but I can emphasize that most all of these methods were shown to be effective mitigation methods. In conclusion, our IF methods are entirely human in the loop. Practitioners control the metrics that they optimize, the techniques they mitigate with, and the size of their perturbations. Future work will focus on applying this methodology to complex models where we might have to find optimal Hessian estimates, build robustness scores for our influential fairness scores, consider second order influential fairness, and lastly, focus on some usability testing. Thank you so much for tuning in.